second of 30 minutes from the field of study tonight. I 13 views, 1 comment. Check out for Takuma, right? Okay, maybe. This new noise, is that worth looking at, do you think? 2 views, 1 comment. That's bound to be my own comment.
Wow. This is what I wanted you to hear or see. Every penny of the rice is free. Yes. Wow. This is what I wanted you to hear or see.
No, okay, so I'm not really doing it. Why am I doing it? I'm doing it disciplining myself to do the next stage of what I was doing last night. So everything's under DeepSeek, right? DeepSeek says, Sophie Gray, philosophical paradox of the ship of Theseus, understanding self-deprecation and effacing comments. If it's a joke at your own expense, it's self-deprecating. If it's modesty stepping aside or downplaying an achievement, it's self-effacing. So got that sorted out. But last night I was talking about asteroid Bennu, and I had an essay that I'd compiled. So this was my text. So I should put myself on camera, but except that I look a right state. But that's rather the point, isn't it? Face cam. Good evening, everybody. No, you see, I'm better off reading without. Put the glasses there in case I need to. Asteroid Bennu's Organic Bounty, a new piece in the puzzle of life's origins. Well, that's not a very good start, is it? Yawning like that. Dear. Analysis of pristine samples from asteroid Bennu, returned by NASA's OSIRIS-REx mission, has revealed a staggeringly rich inventory of organic compounds. The findings are a major breakthrough in support of panspermia, the idea that the chemical precursors required for life on Earth may have been delivered from space. This revised analysis incorporates new details on chirality, mission logistics, and the physical scale of the asteroid. I don't know why we should say this revised, but that's because of the process by which we created it. Okay, so edit required there. Key organic discoveries. The organic compounds identified in the returned Bennu samples and their scientific importance are sugars, nucleobases, and phosphates, the RNA precursor toolkit. The samples contain ribose, a sugar, the nucleobases like adenine, guanine, thymine and uracil, and want the full list there, and phosphate minerals. It is critical to clarify that the samples do not contain the actual constructed chains of RNA or DNA, nor the specific nucleoside monomers like adenosine or uridine. Instead, they contain the separate fundamental chemical components from which those molecules can be built. Finding all of the necessary components together on one asteroid means a Bennu-like object could have delivered a complete chemical starter kit for life to the early Earth. Nitrogen and oxygen-rich polymers, so-called space gum. A never-before-seen ancient flexible material, it reveals some of the earliest chemical reactions taking place in the early solar system and contains organic precursors that could have helped trigger life on Earth, according to reference 1. While a precise gum-to-precursor ratio is not specified, the bulk material of Bennu has a characteristic carbon-to-nitrogen ratio of approximately 20. So for every carbon molecule, there are 20 carbon molecules for every nitrogen. Amino acids, for example, tryptophan. Amino acids are the monomers of peptides, the molecules that build proteins. The Bennu samples contain at least 15 of the 20 amino acids used by life on Earth, including the complex amino acid tryptophan. While simple amino acids have been found in meteorites before, specific complex amino acids like tryptophan had never been definitively confirmed in a pristine asteroidal sample. Previous remote spectral analysis from orbit could only suggest the presence of organics, not identify specific complex molecules. This laboratory analysis is a definitive leap forward. The amino acids discovered on Bennu are found in a racemic mixture, a balanced 50-50 mix of left-handed and right-handed D forms. Life on Earth exclusively uses the L- or levorotatory, the left-handed form. Don't invent words when you're reading them out. This indicates that while these objects delivered the raw ingredients, the selection for life's left-handed preference likely occurred later in Earth's prebiotic environment. It's not the best of sentences, is it? Other compounds. The samples also contain thousands of other organic compounds, including ammonia and abundant water-bearing clay minerals. Asteroid Bennu is a near-Earth rubble pile asteroid with a mean diameter of approximately 500 meters. It orbits the Sun every 1.2 years, or 436 days, bringing it close to Earth approximately every 6 years. The OSIRIS-REx mission was a precisely choreographed 7-year journey to retrieve samples from the distant world. Launched on September the 8th, 2016, and assisted by an Earth gravity flyby in September 2017 at a distance of 17,000 kilometers, it arrived and entered orbit at Bennu on December the 3rd, 2018. Sample collection took place on October the 20th, 2020, at the Nightingale site. There's much more story to that then, because it actually descended with one part of the spacecraft and then the sample return departed from Bennu on May the 10th, 2021 and was delivered back to Earth in September 2023. The capsule landed at the Utah Test and Training Range. The scientific significance and the path forward. These discoveries fundamentally advance the RNA world hypothesis. While Bennu itself did not seed Earth, it is a pristine preserved fragment of a larger water-rich parent planetesimal that was shattered early in the solar system's history. Another fragment from that same body, a Bennu-like asteroid, could have been the very type of object that collided with the pre-biotic Earth, delivering these essential ingredients. The findings provide the strongest evidence yet for molecular panspermia, demonstrating that asteroids were, and probably are, capable of supplying the complete suite of raw materials for life. The OSIRIS-REx samples act as a time capsule, allowing scientists to study the specific chemical pathways that have formed these organics. Ongoing research will now focus on understanding how these separate components could have combined on early Earth to eventually form the complex polymers of life. So I asked, is it possible that it's a fragment of the moon? Is it possible that it's a fragment of the early Earth? Or is it possibly a fragment of a thing called Theia, I believe, which collided with Earth? Pretty monstrous collision with Earth. I think the one that opened up the Pacific Ocean and that sort of thing. Could it be that? But the geology suggests no, chondritic material comes from the outer part of the solar system, not the inner part of the solar system. And what occurs to me that I haven't asked is it possible that these things have formed in such superabundance in the 4.7 billion years, 4.7 billion years that Bennu has been orbiting around, and like it's pristine, but it has also had 4.7 billion years to pump up the volume. In other words, are we saying that the molecules that are in there have been trapped for as long as they have been trapped? No. What are we saying? Were these things synthesized 4.7 billion years ago? Just because we have recovered a piece of rock that is 4.7 billion years old, is it possible that they have been synthesized since the rock formed? How do we know that these things that are present today were around Yeah. Planets are quite interesting, really, in the sense that all sorts of chemistry goes on, All sorts of chemistry goes on. It's like if it can go on, it does. At the chemical level, isn't it? Well, so long as your planet is stirring itself up. There's a big distinction between Bennu, which doesn't stir itself up very much, I think, because it's come from the colder part of, and it doesn't have a magmatic core. It's a rubble agglomeration. It's just sort of formed by particles attracting themselves through gravity. Very, very and we know there's not much gravity in space. Weightlessness, so to speak, right? You've heard of the late heavy bombardment. There's some suggestion that Bennu's temperature is only minus 500. Was the sun warmer or colder? 4.5 billion years ago. Better ask that question. So, was the sun warmer or colder or what should we say 4.5 4.5 not 3.5 4.5 billion years ago. And fancy asking that sort of question. Lord Kelvin would turn in his grave, wouldn't he? He would say, I have to identify a mechanism by which it is and how it would be, and I have to do some calculations, but the AI will do this for us. The faint young sun paradox, and why early Earth wasn't frozen. Seems scientifically engaged. Intense outgassing. What actually? The early solar system environment is directly relevant to our discussion about asteroid Bennu. Well, of course, that's why I'm asking, you silly thing. The colder, fainter sun meant the snow line, the distance where ice can form, on Earth we're talking about presumably, was much closer to the sun. This allowed water and volatile rich asteroids like Bennu's parent body to form, and persist in the inner asteroid belt. The delivery of water and organic materials to Earth by these asteroids to the early Earth would have been crucial, not just for the chemistry of life, but also potentially influencing the early climate and the stability of liquid water. The stability of liquid water. Meaning what? No, I don't want you to explain the fact that it's going to get hotter in the billions of years, because I do know that. It's a terrifying thing, one of those things that you learn when you're about 9 years old, and it terrifies you completely because you know you're not going to live forever, even if you reached 1,000, 1,000,000 years old. So your life is limited, apparently. No, what do you mean about what do you mean about the stability of water? What are you getting at? With the quote, stability of water. Water, unquote. Question mark. It'll say. It will say, oh, the user does not want this and is following up on my earlier point. Asking me to clarify the connection I made between the faint young sun and the stability of water. Everyone clear what we're discussing at this point in time? In the context of asteroid impacts, they seem to want a more direct explanation of the physical relationship rather than just restating the paradox. Yes, of course I do, because I need to explain how the early sun's lower luminosity created a delicate energy balance for liquid water on Earth, and how asteroid impacts fit into that balance. What essentially we're talking about here is that the precursors for life on Bennu take place, are synthesized in a reducing atmosphere in a reducing atmosphere at near in a waterless mix, possibly inside this space gum, whatever that is. Clear mechanistic. Okay, well, clear points to cover are the narrow temperature window for liquid water under a faint sun. It's going to depend on the pressure of the atmosphere as well, actually. But Bennu could have synthesized huge quantities of, or Bennu's the planetesimal of which Bennu is a remnant, the highly fragmented could have rained vast quantities of precursors onto the Earth. Would they survive entry into the Earth's atmosphere? The asteroids would be more likely to deliver because they're not experiencing an oxygen-rich atmosphere. They're being maintained in the same no, not in the same. Yeah, well, they were formed in reducing conditions, and they are being heated and reheated in. Okay, so does the reheating process possibly caused them to evaporate and polymerize. Was the planetesimal's orbit around the Sun quite conceivably highly eccentric, hence leading to its early demise or collision with other objects and then raining down on Earth? Late heavy bombardment. Excellent and precise question. When mentioning the stability of liquid water in the context of faint young sun, I was referring to the delicate and dynamic energy balance on Earth. Critically less energy. Yes, of course. For liquid water to exist, not as temporary puddles but as persistent oceans, the planet needed a very efficient blanket, greenhouse, to trap the heat. Without a strong greenhouse effect, Earth would have been a permanent snowball. Stability of the ocean environment was therefore fragile and could be tipped by major events. Dual role of impacts. Asteroids like Bennu became fascinating. Their collisions with early Earth weren't just delivery of events, they were major climate forcings that could push the balance in two opposite directions. Short-term cooling, long-term warming. Oh my gosh. Short-term cooling destabilizing. The massive amounts of dust and aerosols ejected into the atmosphere from any large impact would block sunlight. Rapid cooling and potentially freezing could trigger a freeze event. Carbonaceous atmospheres like Bennu are rich in carbon, sulfur, and water. On impact, these volatiles would be released into the atmosphere. Carbon? Well, carbon's not a volatile. Carbon's not a volatile. You could argue that if it was rich in carbon, raw carbon, what kind of carbon? Graphite. Carbonates, sulfates, and water. Carbonaceous asteroids are rich in... Okay, I think strengthen the enhance why compensating for the faint sun because carbon dioxide and methane would be released. Yeah, okay, so this is why analyzing it is so revolutionary. For the first time we can precisely quantify, yes, the inventory of carbon, sulfur and other volatiles a specific type of impactor would have delivered. We're moving from theory to hard data. Bennu's material is 4.7% carbon by weight. Scaling up a kilometre impact of this type would deliver millions of tons of carbon. This allows climate modelers to run much more accurate simulations of the post-impact environment on early Earth or Mars. In essence, the stability of water refers to Earth's ability to maintain liquid oceans over eons despite a faint sun. Asteroid impacts were a likely key double-edged sword regulating that stability, first threatening it with impact winters, then potentially securing it by replenishing the greenhouse gases needed to stay warm. Right, so early Earth had a reducing atmosphere. If life precursors were synthesized off planet, hyphen planet, they would have a much higher probability of they would have a much higher probability of surviving entry in the it's not re-entry. See, I don't want to use entry. Surviving impacts. The heat stress of passing a collision with Earth. Collision with the Earth atmosphere. With the early Earth. Also, comment on the atmospheric pressure. A low pressure early Earth atmosphere, early Earth atmosphere would mean water thawing. Reduce heat. Reduce friction. I can't see, however, how it would affect the temperature of water. Could it? Higher temperatures? At lower temperatures? I don't think so. More water in the atmosphere. I cannot see it would mean water through it, but it could, but it would affect evapotranspiration. Evapo. Oh, please, come on! I cannot see it could mean water thawing, but it would impact on evapotranspiration, question mark. Yeah, that's going to give it enough of a prompt. Flippin' heck. It's going to say you're a fucking genius now. Advanced concepts here about early Earth conditions and pre-biotic chemistry survival. They're making two distinct but related points about atmospheric composition and pressure effects. Off-planet synthesis makes sense because early Earth's reducing atmosphere would help them survive impact heating. I need to confirm this is correct while adding nuance about how impacts actually deliver materials. The fact that most meteorite material experiences surprisingly low peak temperatures despite fireballs. Really? Most meteorite material experiences surprisingly low peak temperatures. Good, alright. For the atmospheric pressure point, the user is absolutely right about reduced friction during entry, but I should clarify that while pressure doesn't change freezing point, it dramatically affects phase transitions and evaporation rate. Connect this to the faint young sun part. Yeah, do it. Thinking like an astrobiologist here, so I should structure this as building on their correct insights. You have raised two excellent and interconnected points that get to the heart of early Earth's unique environmental conditions and how they affected the delivery and survival of prebiotic materials. Here's a breakdown of your insights supported by context. Reducing atmosphere and impact survival. You're absolutely correct. The strongly reducing atmosphere of early Earth, rich in methane, ammonia, hydrogen, and water vapor with little or no free oxygen, was a critical factor for the survival of complex organics during the impact events. Notice it says was rather than would be a critical factor. Okay. So it's really accepting that these organics were delivered by, but that is okay. Impact heat shield. A thick reducing atmosphere acts as a better buffer against the intense heating of the atmospheric entry. It can help dissipate heat, potentially allow more material. I would say it could also synthesize. Chemical protection. More importantly, the absence of free oxygen meant the delivered organics were not immediately oxidized on impact, burned up on entry or upon reaching the surface. Exactly. In an oxidizing atmosphere like today's, complex organics and meteorites are heavily degraded, the reducing environment providing a chemically compatible landing zone. The delivery window. Research shows that much of the fragile organic material in carbonaceous chondrites like benus is protected only inside the meteorite's matrix. Only the outer layer is vaporized, creating a charred fusion crust, while the interior can remain cool. Your point strengthens the argument that the period before the Great Oxidation Event 2.4 billion years ago was the optimal delivery window for these compounds. Your second point, atmospheric pressure and its effect. Your reasoning about pressure is sharp. Let's separate the effects on friction and entry. Correct, you are right. Lower atmospheric pressure, less aerodynamic drag. While this might seem to reduce heating, the effect is complex. Lower density also means what then? Less convective cooling, yes. However, the primary thermal protection for meteorites is ablation. Good word to know what that means. It means burning off the outside layers, yes, which still occurs. The overall survivability of impacting material will be influenced by a combination of entry, angle, velocity, and atmospheric composition, and more than pressure alone. On freezing point. Correctly noted, atmospheric pressure has a negligible effect on the freezing point of water. The phase change from liquid to solid ice is barely affected by the range of atmospheric pressures considered for early Earth. On evaporation and climate, though, which is a key insight, this is where your point becomes crucial for the faint young sun paradox. A lower atmospheric pressure would indeed lead to much higher rates of evaporation. Water would transition from liquid to vapor more easily. The problem, this creates a bigger climate puzzle. More water vapor in a cold atmosphere leads to more ice clouds, which increase planetary albedo. Fancy that! Reflectivity. Cooling the planet further, the opposite of what's needed to solve the faint sun problem. The likely solution that this is strong indirect evidence that Earth's early atmospheric pressure was likely not lower, but possibly even higher than today's. A higher pressure atmosphere, rich in greenhouse gases like CO2 and CH4, would suppress evaporation rates, create a stronger greenhouse effect to warm the planet, provide the necessary conditions for stable liquid water oceans despite the sun. In summary, your thoughts align well with current models. Of reducing potentially denser atmosphere was likely essential. Okay, so visualize these factors. The faint sun. It provided a chemically benign and physically protective environment that maximized the delivery of intact organics while simultaneously solving the climatic puzzle of liquid water stability. See the following diagram. Well, we can do that, but except I can't. Let's try. Not easily. Would I like to go into more detail? Not tonight, thank you. It's about time I stopped this video. Critical question. Liquid water stability. Reducing atmosphere, no free oxygen, likely higher pressure with a stronger greenhouse effect. Warmed planet solved the faint sun paradox. Stable liquid oceans. Protected delivered organics from oxidation and heat. Preserve the prebiotic chemistry. Window for life's emergence. Save. Okay, what did that take? 42 minutes from the field of study. Jeepers.